Okay, so bonding and structure in elements. First of all, it might be worth clarifying exactly what we mean by these two different words. So bonding is all about different ways in which atoms can stick together, the different explanations that we have for how the atoms, separate atoms of an element, can join together. Structure is more about the bigger picture, and once atoms have joined together, what does the broader structure look like? Hopefully that'll be clear in the next couple of slides. When it comes to bonding, in elements we only have two types, metallic bonding or covalent bonding. So metallic obviously happens within metals, covalent is bonding within non-metals. Ionic is the other type of chemical bonding that we know about, but that can only work in compounds typically when we've got a metal and a non-metal. So structure, there's three different types we need to consider when it comes to bonding and structure in elements. Metallic bonding always comes with a lattice structure, so that one's really easy. Metallic and lattice go together. Metallic bonding, lattice structure. For covalent bonding, we have two different types of structure. So we could have covalent bonding and a molecular structure, or we could have covalent bonding and a network structure. What I'm going to focus on in this presentation is what happens when each of these different structures melt or boil, when elements with each of these different structures melt or boil. Okay, so in metallic lattice structures, we've got these positive metal ions surrounded by a delocalized sea of electrons. Now, one thing that's really important to remember is that even though there's only 12 atoms drawn here, a metallic lattice structure you can think of it as almost infinite. Even in the smallest little piece of metal that you could pick up, there would be billions and billions and billions of atoms. So this is a really, really, really small little snapshot of a much, much bigger structure. When we talk about metallic bonding, what we're talking about is, remember I said bonding is all about how the atoms stick together. So metallic bonding is the force of attraction between these positive ions and these delocalized outer electrons. Remember, it's the outer electrons that are delocalized in a metal. So bonding is about the stickiness, it's the force of attraction between the positive ions and the delocalized electrons. The lattice structure refers to the fact that we've got nice regular rows. It's a nice, neat, regular structure, and it also extends almost, we could almost say infinitely, because there's billions of atoms in a single piece of metal. Right, so when the metal melts, the positive ions have enough energy to move freely. So we can think about this as almost like if each of these was a little marble, it would be like the marbles, we could move them around, but they weren't completely separating. So melting disrupts the metallic bonding, but it doesn't completely break them. When a metal boils, however, the metal atoms separate and the metallic bonds are completely broken. So that's what I've tried to show with these little yellow circles and arrows. If you can imagine the atoms that are surrounded by these yellow circles, them becoming completely separate, like we've spilled our marbles all over the floor. They're completely separate, and when a metal boils, the metallic bonds are completely broken. What you really need to know is that the melting and boiling points of metals indicate the strength of the metallic bonds. So when we're talking about metallic bonding, no other words are relevant really. We don't talk about anything to do with molecules, we don't talk about intermolecular. Metallic lattice structures only contain metallic bonding, and the strength of the metallic bonds is indicated by the melting and boiling point. So the higher the melting and boiling point, the stronger the metallic bonds, and the harder it is to pull these atoms of the metal apart. Right, so in covalent molecular structures, the key thing that you need to remember is that we have strong covalent bonds which hold the atoms together in the molecules. So in the picture, the little orange blobs represent two oxygen atoms joined together. They are joined together by a double covalent bond. So covalent bonds are always strong. Strong covalent bonds hold individual atoms together in molecules. It might be a diatomic molecule, so like this with oxygen only containing two atoms, but it might be a molecule containing more than two atoms. So a molecule is a kind of, what we would maybe say is a discrete entity. A molecule can just go about on its own. It's quite independent of the rest of the molecules. But when we have a solid molecular structure, we do have weak intermolecular forces holding the molecules together. So I haven't represented these, but you can imagine each little molecule almost as like a little magnet, and when you bring them together, the little magnets click into place if the temperature is low enough, and they can come together as a solid, but you could then separate them back out again, and you'd still have the original magnets just as they were. So when a molecular substance melts or boils, when it boils and becomes a gas, you still have these strong covalent bonds holding the atoms together. It's only the weak intermolecular forces which have broken. Because of this, the melting and boiling points of molecular substances give us an idea of the strength of the intermolecular forces, because that's what's broken when the substances melt or boil, not the covalent bonds. Right, in a covalent network structure, one thing that's important to remember is this is not a molecule. The reason it's not a molecule is that whilst we do have covalent bonds connecting up all the atoms, in any one tiny grain of a covalent network structure, even a grain of sand, so silicon dioxide is a covalent network, even in a grain of sand there are billions and billions, too many atoms really for us to count, so we don't consider covalent network structures to be molecules because they're so big. So what we've got is these atoms connected together by covalent bonds, and these strong covalent bonds extend throughout the structure. So that's what makes the difference between a molecule and a network. Molecules, the covalent bonds are within the little separate packets, the little separate molecules, but in networks, the strong covalent bonds extend throughout the structure. Because the covalent bonds extend throughout the structure, going from one to the other, to the other, to the next carbon atom, in this case with diamond, you have to break these covalent bonds to melt or boil this substance. So remember, when we melt or boil something, you're imagining the particles separating and coming apart. In a molecule, we can separate the separate molecules, but in a network, we can't separate anything other than the individual atoms. That means we have to break these strong covalent bonds to melt or boil the network. Covalent bonds are very strong, hence this requires a lot of energy to break down this covalent network structure, allowing these substances to melt or boil.